Hi everyone. We are the Algorithmic Fairness team focusing on countering implicit bias in the admission process. Our team members are Zeyu, Shen, George Wang, and Xingyu. Our team is being advised by Professor Kamesh Mangala and Professor Brandon Fay. So let us begin with a very simple example demonstrating how implicit bias is negatively affecting the admission process. So considering this scenario where we have 4 applicants, Alice, Bob, Catherine, and David, competing for 2 slots in the school. Suppose that Alice and Catherine are from the minority and Bob and David are from the majority. We assume that each of the applicants have a true underlying cardinal score, which denotes their ability, and the school should be admitting them based on these scores. Now suppose there is no bias, then Catherine and David have the highest scores, and the school should admit Catherine and David directly. But however, consider another scenario where there is some sort of implicit bias, in which the minorities are being scaled down by 0.5 on their cardinal scores. So on the perceived scores of so in this scenario, the perceived score of the minorities are being scaled down. As you see, Alice is now 0.15 and Catherine is now decreased to 0.3, which is actually smaller than Bob, which is 0.4. So in this scenario, the school will choose Bob and David instead, and Catherine, who should have been admitted, is not being admitted in this case. To formally study this sort of like negative impact of implicit bias in the admission process, we need to characterize the damage of implicit bias in the following ways. The first way of characterizing it is to use a notion of cardinal score loss, which denotes the difference between the actual cardinal score that is obtained if there is no implicit bias and the cardinal score, summation of cardinal score of the applicants that are admitted when the school is making the decision with presence of implicit bias. So in this scenario, it's just 0.2, which is the sum of the raw cardinal score of Catherine and David, which is 1.4 together, minus the summation of score of Bob and David, which is 1.2, which will result in a difference of 0.2. Another metric that is being considered is called instability, which is basically the difference between the number of minorities that should have been admitted and the number of minorities that are actually admitted. In this case, the instability is 1. To formally study this sort of implicit bias, we usually consider a function, which is called the bias function, mapping from the actual score of applicants to the observed scores perceived by the school. So this function usually satisfies the following 2 properties. First of all, it's order preserving in the sense that it is monotone. And secondly, it does not strengthen the protected group or the minority in the sense that mathematically, the bias function is upper bounded by the diagonal linear function, which goes from 0, 0 to 1, 1, as shown by the blue line. In previous works, people usually study the bias. People usually model the bias function by a beta linear bias, in which every applicant, the cardinal score of every applicant, regardless of their actual cardinal value, is being scaled down uniformly by a factor of beta, where beta is between 0 and 1. In our work, we consider a more general form of bias, which we call beta max weakest bias. The beta max weakest bias is essentially the upper bound of all bias functions that is upper bounded by beta max. Well, there are numerous ways to counter the implicit bias, and some of them are being put into use in reality. The most famous one is called the Rooney Rule, which is basically saying that regardless of scenarios, at least one of the minorities must be considered in any sort of interviews. This rule is being used in the coaching interviewing process in NHL and NFL. A generalizing rule from the Rooney Rule is called the majority quota, which basically gives a lower bound on the number of minorities that are admitted. And a very common and natural derivation of the majority quota is called the proportional rule, which sets the quota of the minorities to the proportional to their percentage in the entire population. Another generalization of the majority quota is called minority reserve, which is similar to the reserve system in class choosing at Duke. It does not make a significant difference in the single school case, but it does not require does not require the minorities to fully reach its lower bound. Despite the common usage of implicit bias intervention methods in reality, theoretical research has not been done until last decade. In 2011, Hafali et al. Proved that minority reserve is better than majority quota in any scenarios. And in 2018, Kleinberg et al. Proved that for sufficiently large linear scaling bias, the Rooney Rule would always yield a better result in terms of Cardinal score loss compared to doing nothing. And in 2020, Celis et al. Proved that for sufficiently large population and linear scaling bias, the proportional rule will always dominate.
Then we introduce how we will model the admission process. In our work, we will focus on the single school setting where there is only one school and the students can only apply to this school. Essentially, there are small m minorities and big M majorities, where small m is less than big M. Each student has a cardinal score, which denotes the ability of the students that is drawn from a uniform distribution from 0 to 1. Here, the score is interpreted in the sense that the higher the score is, the better a student is. So the more probable the student is to be accepted. The school has capacity Q, where Q satisfies Q less than big M plus small m. Also, the school will enforce a minority reserve of R. That is, the school will at least accept R minorities. Then we provide the following illustrative example. We still consider the case where there are 4 students, A, who is a minority, B, who is a majority, C, who is a minority, and D, who is a majority. And the school wants to accept Q equals 2 students. We recall that without reserve, the school will accept Bob and David because the Catherine is biased down to 0.3. So the top 2 students with perceived score are B and D. However, if the school enforces a reserve 1, then Catherine and David will be accepted because the school will prioritize the first accepted minority, who is Catherine. And we can see that here, the optimal admission result is recovered by the reserve. Then we have the following question. How can we set a reserve, or even how can we determine whether a reserve is good or not? Essentially, there are 2 different views. In the first view, we want to maximize the utility that is result from the reserve. That is, we want to maximize the sum of the true ability of the accepted students. From the previous work, it has been shown that setting R to be the proportional number of minority students in the entire population is asymptotically optimal for large M. And the second choice is to maximize the stability. And in other words, we want to minimize the number of students who should have been accepted but did not. Here, we note that such student can either be majority or minority. And from our experimental result, we have seen that setting R to be the proportional number of minority students is still optimal here. And ultimately, we note here that when there are finite number of applicants, the proportional rule might not be optimal at all, but it will still be kind of close to optimal. So our next theorem will show how close it is to the optimal solution. Here we look at the following theorem. We first recall the following notations. There are small n minorities, big N majorities. The capacity of the school is Q, the reserve is R, and the beta is an arbitrary bias function with upper bound beta max. Here, beta max is a constant, and beta is a function such that beta x is always less than beta max. Also, we use E of R to denote the expected number of students that should have been accepted but did not, given R reserves. Also, we use OPT to denote the minimum value of E of R among all R. Then we have the following theorem. When beta max is upper bounded by some value, then we have the expected number of students that should have been accepted but did not under the minority reserve is very close to the optimal solution. As an example, say there are 1,000 majorities, 100 minorities, and the school want to accept 100 students. You can see that even when epsilon is very small, the beta max is still kind of large, which shows that our theorem can apply for a wide variety of bias functions. And when epsilon gets larger, the beta max will correspondingly get larger.
Other than using minority reserves, you could also try to recover the distribution of the minorities. So suppose the majority students follow a distribution D1 and minority students follow distribution D2 perceived by the school. The goal of this model would be to apply an affine transformation to D2 such that the distance between D1 and D2 is minimized. So a canonical way is to align the mean and standard deviation of the two distributions. There are more advanced ways which we will consider in the future. So we ran this experiment on 200 majority students, 100 minority students, and variance capacity as independent variable. The linear bias, we first consider like the case of linear bias function, which with a fairly low beta, 0.4, and then with a extremely high beta, 0.99. And we could observe that there are cases when the affine loss is lower than the proportional loss and vice versa. And as for the case of the weakest bias function with low beta, we can observe that the affine loss is always greater than proportional loss, meaning that the proportional loss dominates the affine loss in this case. Actually, using beta as 0.99 in the weakest bias function is almost identical to the linear bias function with beta 0.99. So we do expect such a graph as the lower part to exist. And for future works, we hope to make the algorithm data driven by inferencing the beta max. And then we hope to extend the proportional rule to multiple school setting and probably with finite students. Last but not least, we will try to implement some other matrices for the affine transformation of the distribution so that the distribution we recover is more descriptive. Thank you for your attention.